Okay, welcome to today's Math 1101 class. We're going to be looking at the basic derivative rules. These are shortcuts to the method we were looking at last day, which was called the delta process, or the definition of the derivative. You only need to use the definition of the derivative or the delta process if the question specifically asks you to go ahead and find the derivative using that method. Most of the time you can use these shortcut methods to find the derivative, and you're going to find that they're pretty easy in this course. You're only looking at derivatives of polynomial functions anyway. We're going to start on page 27, and the first rule that we're looking at is called the constant rule, and this is pretty straightforward. A constant function would be just something like y equals 4. That's a constant. And in fact, y equals 4, you might all remember, is nothing more than a horizontal line. Here's an example right here in this graph, a horizontal line that looks like it's probably y equals 2 there, or y equals 10, depending on how you look at the scale. But anyway, you can see that a horizontal line has a slope of 0. And seeing that's what the derivative is, it's just a slope function. Well, people, there is your first rule. If you just have a constant function, y equals 4, or any constant, even if a constant is part of a longer function, the derivative of that piece is always 0. And that's your first rule. Here's another important rule down here on the bottom. This is called the power rule. And it says that if you're taking the derivative of some base to some power, and let's suppose that the base is your x, of course, so x to the power of n, for example, y equals x to the power of 6. Okay, so if you were going to apply the power rule here, here's what would happen. The 6, which is your exponent, actually comes down, it moves down in front of the x, like so. And that might look familiar to some of you as something, there's a logarithm rule very similar to that, a law of logarithms, but it's not quite the same thing in this regard. Now, according to the rule, the power is 6, but you subtract 1 from that power, and so the power turns into 5. The derivative of x to the power of 6 is 6 times x to the power of 5. On page 28, they have some examples of these, and the first three are rather straightforward. You'll notice y equals 5. Well, people, y equals 5 is a constant. F of x equals e. Well, people, e is just a number. You might recall it's the base of the natural logarithm. Even the sign of 2 pi, well, people, there's no variables in there. That's just a number. In fact, the sign of 2 pi, if you were to actually type that into your calculator, you would get 0 for that. But the thing I'm trying to say is they're all functions. So for all of these, the derivative is 0. F prime of x equals 0. Now you'll notice that the third example C there, they haven't actually written that using like a function notation. They don't have y equals, they don't have f of x equals, they just have a term, sine of 2x. So one way you can show that you're taking the derivative of that would be d dx, and then in your brackets, sine 2 pi, like so, and of course now the answer, because again it's just a constant, you just get a 0. Down below that, you have some other examples. These are straightforward applications of the power rule. So if y is equal to x to the power of 3, your derivative becomes 3 down in front, x to the power of 2. There's your derivative. If f of x is equal to x to the power of 8, the derivative becomes 8x to the power of 7. All right, 8 down in front, write your x. Subtract 1 from the 8, your exponent turns into 7. C is interesting because C, you have just y is equal to x. Well, there is a power there. That x does have a power. The power is a 1. So think of it this way for the third one. Y prime is equal to, the 1 comes down in front. You still have your x, but then 1 subtract 1, you get an exponent of 0. Well, people, this, anything to the 0 is just equal to 1. So in fact, y prime is equal to 1. That's your derivative, just 1. And think of this as a linear function. In general, if you have any linear function like y is equal to 7x, for example, your derivative is just the coefficient that's in front. So your derivative there would just be 7. And d is simple. F prime of x, use your power rule. 2x is all that you have there. 2 comes down in front, x. 2 subtract 1 is 1. There's no need to write the exponent of 1 there. Two more rules on the next page, and these are actually fairly straightforward. The constant multiple rule is just basically another case of your power rule. What if you have a function where there's already a number in front of your variable part, like so, 5 times x to the power of 3? Well, what are we supposed to do there to take the derivative? Well, the derivative becomes, the 3 still comes down in front, as before, but now it gets multiplied by the 5, turning into 15. Your x now becomes x to the power of 3 subtract 1, and you get 2. And there's how you take the derivative there. It's actually very straightforward. Nothing to that one at all. And the sum and difference rule is also very straightforward. All it says is that if you're taking the derivative of a long polynomial, like a trinomial or a binomial or anything like that, you just take the derivative of each individual piece of your polynomial. You apply the derivative rules, whatever they may be, however many terms you have there. It's very straightforward. Now the examples on the bottom of page 29, some of those are rather tricky. Some of them are a little bit, I won't say difficult, but they can be tricky if you don't think carefully. Remember that all the solutions have been posted on D2L for these in case I run out of time. But the idea to getting all of these done correctly is to first write them all as exponents. So if you see y equals the square root of x, you should write that as x to the power of 1/2 first. X to the power of 1 over 2. My pen is not working very well. If you have f of x equals 1 over x, you write that as x to the power of minus 1. Minus 1. There you go. Y is equal to x times the cube root of x. Well, that you should call y is equal to x multiplied by x to the power of 1/3. That's what the cube root is. And of course, the x by itself actually has a power of 1 beside it. So your original function would be y is equal to x to the power of 4 over 3. And now you use your derivative there. So the derivative of y prime would be 4 over 3 in front, x to the power of, and 4/3 subtract 1 is, whoops, not that. I'll just erase that. Is x to the power of 1/3. Learning to use this pen is not the easiest thing. Again, the last one there, x over the square root of x, or the second last one, write that as x multiplied by x to the negative 1/2. Add your two exponents together, so your original function there is y is equal to 1 plus negative 1/2 is x to the 1/2. So it's just the square root of x. Actually, it's exactly the same as the first one here. Exactly the same thing. Your derivative would become 1/2 x to the negative 1/2. Like so. And for the last one, break this up into two pieces. X squared over x squared, so you get y is equal to 1 minus, and 3x over x squared would be just 3 over x, which is 1 minus 3 times x to the negative 1. Your derivative would become, I'm all over the place here, 0, because that is 1 is a constant, and minus 3x to the minus 1 would become plus 3x to the negative 2. So there's your derivative, just 3 times x to the negative 2, or 3 over x squared. Now, on the next page, here are some examples that you could be asked. Page 30. Find the derivative of each of the following. A looks fairly straightforward. B looks fairly straightforward. C looks straightforward. Even D will be fairly straightforward. But for D, you should first of all write this as 2x to the negative 2, and then apply your derivative to that. So y prime would be equal to negative 2 times 2 is negative 4. X, negative 2 subtract 1 is negative 3 for your power. You can leave it like that if you like, or you could write it as -4 over x to the power of 3. Now I'm running out of time here, but I'd like to show you the example that comes below that. Find the slope of the curve at the indicated point. In every one of these cases, there's A, B, C, D. You'll notice that you have a function given, and they want you to find the slope of the curve at the indicated point. Now, you know you're going to have to take the derivative there. You have to find your derivative for each of these cases. And then, once you have your derivative, you plug in the x value, which, for example, for the first one, the x value was 2. So you would plug a 2 into your derivative. That would give you the slope of the curve at the indicated point. You could also be asked to find the equation of the tangent line at that indicated point. Again, please note that all full solutions for all of these examples and the practice problems have been posted on D2L. Please make sure you download a copy and look at them. If you have any questions on anything here, please make sure you ask me during our regular class time or during office hours, and I'll get online with you and I'll go step by step and show you how these are done. So let's look at A. I'll do A with you, and I think that I'm going to be out of time. But the first one says y is equal to 9x minus x to the power of 3. As soon as you see slope of the curve in any question, you should know that means you're going to have to find the derivative. Well, the derivative of this first one is actually pretty straightforward. It's a binomial. So all we do is we take the derivative of each individual piece. The derivative of 9x, well, that's a linear function, just 9 multiplied by x. So the derivative of that piece only is just 9. And then we have a minus. X to the power of 3, we use our power rule there. The 3 would come down in front. Then we have our x. And 1 gets subtracted from the exponent 3. So you end up with an exponent of 2. There's your derivative. So now what you need to do is you need to put in x equals 2 and y equals 10. But there's nowhere to put the y in this case. So don't worry about the y. That doesn't go in. Not now. Later on, you'll see some derivatives where you will have to put in the y. So what you do now is you evaluate y prime of 2, which means you put 2 into the derivative. You will get 9 minus 3 times 2 squared. And you just work this out. You just evaluate this. So y prime of 2 is equal to, this becomes 3 times 4, that's 12, 9 minus 12. The answer is -3. So that's the slope of the curve at the point 2, 10. That's the slope of your curve, and you have answered that question. The other ones are similar to that. B looks fairly straightforward. Again, it's a trinomial, but you just apply the power rule here and here. And here you apply the constant rule. So the derivative of that last piece, the plus 2, that's only 0 anyway. So that piece basically vanishes. For C, you should rewrite it as an exponent first, just a power. So your first step would be to do this. Y is equal to, your 4 stays in front, of course. And the cube root of x squared should be x to the power of 2 over 3. Oops. Oh, this pen is not working that well. Okay, that's supposed to be 2 over 3. I hope you can see that. So anyway, now you take your derivative of that and finally plug your x into there. And D is similar to what we did on the previous page. Break this one up into 2 pieces. So y would equal square root of x over x minus x squared over x. Simplify each piece to a simple power. Take the derivative of that, and then you plug in 4 into your derivative. So we're almost out of time. I'd like you to try the remainder of these examples on page 31. That's the only place they have some. But I'd like you to try those, please, and go back and look at the ones that we didn't get a chance to do during this video. And I hope you get something out of this. Like I say, please let me know if you have any trouble on anything. We can certainly go into the virtual classroom, and I can actually write the steps out for you on that on the whiteboard there. Okay, so that's it for our lesson for today. Thank you very much. Have yourselves a wonderful evening.